the Free State province in South Africa for a while had some severe drought, which of course is good for PV modules, sorry ladies and gentlemen, but you know, you don't want too much cloud cover for a PV system. But for the last few months we've been having a lot of rain, and so our system actually got to a point where the battery was drained. It was no longer sustainable because we were just draining it too fast. So we had to optimize a few things there, which is part of a different paper, because if you're going to have a severe cloud movement for 2 weeks, the system can't handle that. The battery is just too small. So we are looking into that at the moment. That's a challenge which we have encountered. So here we can see 2 specific days. Just some interaction, otherwise you fall asleep, ladies and gentlemen. Just a question to you quickly. What do you think is causing this up and down movement? This is a beautiful day. This is a beautiful day. This was, what day? 9th of September. It's a beautiful day. There was I'll give you a hint, no cloud movement here. So what do you think is happening on the left?
Rain?
Ah, yes, not a cloud. There was rain on that day. Yeah, you can see it's going up and down all the time. As the sun breaks through the clouds, it shines back onto the module. However, look, ladies and gentlemen, your degrees. There's our 9 degrees on top. You can see here, this bottom one, that's the 9 degree. It's performing the worst. It's not providing us with a lot of energy. However, as you go up in degrees, tilt angle, you go to the top, you go to this one, 34 to 44, you can see there, you're getting the most out of this module. Remember, it's stationary. We're talking about a stationary module. Many power plants still in South Africa install stationary modules. You do have the dual axis tracking, which is taking over slowly because you do get much more energy out of that, but there are other variables again which need to be considered, especially when it comes to mechanical strength, and of course wind plays a major role on a tracking system. Alright, so if we just look here, ladies and gentlemen, we can see just some results. So you can see that the highest yield, this is counts above 16. Remember, it's a 20 watt module. So we want to try and get as close to that 20 watt as possible out of the system. So you can see that here, so counts above 16 watt, 400 of them were achieved by these 2 tilt angles. Which are these two? 34 and 39. They achieved the highest output power. We can also see this graph, this line over here, lines over here, that counts above 16. We also have the average, that's the average as we spoke about there, and the median is a little bit lower, but the standard deviation you can see is quite high. Why? Why is the standard deviation high? Well, you've got to remember that the panel starts working early in the morning until late in the evening. If there's sun, it's working, but it's not working optimally. It really only works optimally between about 9 and 3 in the afternoon, but you've got this wide variety of results that you're getting. In the morning you can maybe get 1 watt out of the module, and midday you can get 16 watts. That's why you always have a high standard deviation when we're looking at the results. Now we can just look at the maximum. Which tilt angles gave us the maximum for a specific day? 29 and 34, those two. Now of course 29 is a research site. This is September, so we're heading out of our winter. We're basically in the spring, we're heading into summer. So research shows that in winter months, your tilt angle should be higher than your research site, which is higher. I mean, 34 is higher than 29. As you move into summer, your tilt angle should decrease, because of course it's the height of the sun and the movement of the sun. So we are happy to say that our results are in line with research that has been done in the field already. And it also shows, especially if you look at the previous one, there, we are following the solar radiation curve of the day. That's what the normal solar radiation curve will look like. Of course, that's for the year, it will be like a sine wave, right? Up in December, or up in summer, and down in winter. This is the annual solar radiation curve. So, our objective was to try and put this jig together, to see whether the results we get from it are valid or trustworthy, so that we can duplicate the jig and distribute it to a number of sites, and of course at the end of the day to either validate simulation results or to validate a renewable energy system which has been designed. And of course the data, we can be able to analyze or get that data wherever internet activity is available, because Google is what? So our validity was proven by our daily solar radiation curve, also research that shows in winter it should be higher, the tilt angle, and in summer it should be lower. Our data is tending to show that. we only have the one module with the one load, and in this case our load is a LED regulated load. Previous research has shown that an LED can be used as the load for these small picker systems. And again, as we said, we want to verify simulation results and a design of a system. Thank you.